and get started on today's lecture. I had a couple more problems to do in section 4.2, and actually one problem left to do in section 4.2, but pretty much we're moving on to section 4.3 and 4.4 today. Today's an important day in the life of derivatives and stuff. So, let's go ahead and get started on this. This was the last problem in section 4.2 I did not get to. Suppose that f of x is continuous on the interval between, and I'm going to change these numbers up because I've got too many 2's and 8's floating around here. I randomly chose a problem on WebWork and it just gave me the same numbers. So I'm going to change these numbers here. Let's change, okay, continuous on the interval between 2 and 8, and let's let 3 be less or equal to f of x, which is less or equal to 9. That will just be different numbers, so you're not confused by which number goes where. All right, so here's the deal. Suppose f of x is continuous on closed interval between 2 and 8. And 3 is less or equal to f prime of x, which is less or equal to 9. For all x in the interval between 2 and 8. Use the mean value theorem to estimate what f of 8 minus f of 2 is. Now, if you remember the mean value theorem, it stated that there exists a c in the interval between a and b such that f prime of c would be equal to f of b minus f of a over b minus a, provided that that the function was continuous on the closed interval, it was differentiable on the open interval. So we had all these conditions according to this, but this was the big formula. And this was the one we wrote down, but also there was an equivalent formula that stated that f prime of c times b minus a is equal to f of b minus f of a. This is part of that alternative formula for the mean slope formula there. All right, so here's the big deal on this particular problem. This is the formula that we're going to use from the mean value theorem to be able to do this particular problem. Now, here's the deal. Here's the formula. We know that f prime of c times b minus a is actually equal to f of b minus f of a for some c in my interval. What I'm going to do here from the mean value theorem is rewrite this. This f of b minus f of a is on the left side is equal to the minimum value of f prime of c times b minus a. And on the right side, this will be less or equal to the maximum value of the derivative, f prime of c times b minus a. In this particular problem, a was equal to 2 and b was equal to 8. So plugging it into this formula, you've got the minimum value of f prime of c times b, which was 8 minus 2, is less or equal to f of b, f of 8 minus f of a, which is f of 2, which is less or equal to the maximum value of f prime of c times b, which is 8 minus 2. All I did was replace that f prime of c with the small value of f prime of c and the big value of f prime of c. For you see, they gave me some information about the derivative in this problem. The derivative is between, and I changed the numbers, between 3 and 9. The minimum value of your derivative is 3. The maximum value of your derivative is 9. Does that make sense? So the minimum value would be 3, so it would be 3 times 8 minus 2 is less or equal to the f of b, f of 8 minus f of a, f of 2, which is less or equal to maximum value, which was 9, times 8 minus 2. Now all I got to do is basically do some arithmetic. What's 8 minus 2? 6, and what's 6 times 3? So 18 is less than or equal to f of 8 minus f of 2, which is less or equal to, well, 8 minus 2 is 6, and 6 times 9 is 54. Does that make sense? So what are the bounds? See, I can use the mean value theorem to get a handle on the difference in the bounds. So what's the low bound on f of 8 minus f of 2? The low bound was 18, and the upper bound is 54. And it uses the alternative formula of the mean value theorem, using that mean value slope, where you multiply both sides by b minus a is what it comes to. So this is how you end up doing one of these kind of problems and stuff. It's not very difficult, but you actually had to catch a pattern on the minimum value of f prime of c times b minus a will be less or equal to f of b minus f of a, which is less or equal to the maximum value of f prime of c times b minus a. And they're going to tell you what the minimum and maximum values of your derivative are, so you can plug it in. All right, moving on to section 4.3. 4.3 is about derivatives and the shapes of graphs. All right. First off, increasing, decreasing test. If f prime of x is greater than 0 on the interval, then f of x is increasing on that interval. What's the big deal? Well, if the derivative is greater than 0, you got a positive derivative. Remember, the derivative is the slope of the tangent line. So if you're sloping positively, as you read it from left to right, you're going up. You're going up means you're increasing on that interval. If the derivative is less than 0 on that interval, then f of x is decreasing on that interval. The derivative greater than 0, you're increasing. Derivative less than 0, you're decreasing. A critical number is a number of a function f of x, is a number c in the domain such that, here it is, critical number, f prime of c equals 0, or f prime of c does not exist. Remember, there were two ways we found critical numbers. We took derivative, set it equals 0, and solved, and where the derivative didn't exist at. But here's the big deal. If f of x has a local maximum or minimum at c, then c is a critical number. That's what we're after. Max, min numbers, critical numbers. Now, here's the big deal. If you analyze this, what's the critical numbers where the derivative equals 0 at? Now, it's a minimum point. How do you become a minimum? You go down and then you go back up again. To go down means the derivative was decreasing. First derivative is less than 0. You hit your critical point, and then you increase. The derivative is greater than 0. That gives you minimums. And for maximums over here, to maximum you got to go up, then you got to go back down again. To go up, the derivative has to be greater than 0. It means I'm increasing. I hit my critical point, and then I'm decreasing. So the relationship between the derivatives around your critical point will let you know what kind of critical point you have, minimums versus maximums. That leads us into what we call the first derivative test. Suppose c is a critical number of a continuous function f of x. If f prime of c changes from positive to negative at c, then f has a local maximum at c. If f prime of x changes from negative to positive at c, then f of x has a local minimum at c. If f prime of x does not change its sign at c, then f of x doesn't have a maximum or minimum at c. What we're really interested in is this. We're going to be doing number lines on this thing. This will be a first derivative number line. C is where the derivative is equal to 0 at. What you're going to do is you're going to do test points on either side. Pick a number less than c. And you're going to plug this number into your first derivative. And if the number is going, let's say it's going to be negative, we're going to put little minuses up here because it's negative. And then you pick a number bigger than c and you plug it into your derivative. And let's say it becomes positive, greater than 0, positive. What kind of critical point does that make c? Well, the derivative is negative means I go down. If the derivative is positive means I go up. If you go down, here's your critical point, and go up, what kind of point is it? You got it. It makes C a minimum point. Vice versa, if I got C over here and I do a test value, this is the derivative graph, and you do f prime of some arbitrary point less than C, and it happens to be greater than 0, which means it's positive or it's increasing that interval, and you pick a number bigger than C and you plug it into your derivative, and it ends up being less than 0, negative, that means you go down. If you go up, then go back down, what kind of critical point does that make C? Maximum. That is the only way you're going to get minimums, only way you're going to get maximums. If you've got a derivative, you plug it in and it's negative, then you hit your critical point, and then you plug it in some more derivatives and it's still negative, that doesn't make max min points. That'll probably be something called an inflection point later on, we'll get that in a second, but it's not going to be a max min point, which is what we're after. They got to change signs on my derivative. Second derivative test. If f double prime of x is greater than 0 on the interval, then f of x is concave up on that interval. If f double prime of x is less than 0 on an interval, and f of x, then f of x is concave down on that interval. This is what we mean. Your first derivative measures increasing decrease. If your first derivative is greater than 0, that means you are increasing. If your first derivative is less than 0, that means you are decreasing. Your second derivative measures concavity. So if your second derivative is greater than 0, that means it's called concave up. Concave up means it is U-shaped up. It's going to be bent upwards. The rate of change of the rate of change is positive. That means the graph is bent upwards. And if the second derivative is less than 0, that means it is concave down. And concave downward means it is bent downward. Okay? So, putting these two concepts together, we're going to basically going to be looking at what the graphs of these functions are going to look at through their derivatives. Increasing slope means the first derivative is greater than 0. Decreasing slope means your first derivative is less than 0. Concave up means your second derivative is greater than 0. That's U-shaped up. Concave down means your second derivative is less than 0. That means it's concave down. So when you start blending these two concepts together, first derivatives with their second derivatives, this is what you get. If you are increasing, positive first derivative, and it's concave up, bent upwards, you've got to increase and be bent upwards. This is what your graph looks like when the first derivative and the second derivative are positive. If you're increasing, means your first derivative is positive, but your second derivative is negative, is concave down. I've got to go up, but I've got to be bent downwards. This is what your graph looks like. It is going up, but is being bent downward. That is increasing, concave downward. Decreasing means my first derivative is negative. If it is concave up, second derivative is positive, I got to go down, but I got to be bent upwards. This is what that section of graph is going to look like. It's going to be going down, but be bent upward. And last but not least, if the first derivative is negative, it's decreasing, and the second derivative is negative, it's concave down. I got to be going down, and I got to be bent downward. This is what that section of graph looks like. So it's a blending of the two graphs, increasing, decreasing, concave up, U-shaped up, and concave down, U-shaped down, to get these pictures. And this is what we're going with. More definitions. An inflection point of a function f of x is a point at which the curvature, second derivative, changes signs. The curvature changes signs from being concave upwards, positive curvature, to concave downward, negative curvature, or vice versa. And basically, you may U-shaped up, U-shaped down, or you could be U-shaped down and then U-shaped up or something like that. These points right in here are the inflection points. And pretty much how do you find inflection points is by taking the second derivative, setting it equal to 0 and solving. But to be an inflection point, you got to change concavity. You got to go from being concave up to concave down, or from being concave down to concave up. So you get that basically that little U up, U down difference look right between the two. That's called an inflection point. Typically found by taking the second derivative, setting it equal to 0 and solving. And then the last little thing is called the second derivative test. Suppose that f double prime of x is continuous at c. If f prime of x is equal to 0 and f double prime of x is greater than 0, then f of x has a local minimum. Let's put the two concepts together. What do you call it when f prime of x is equal to 0? X is equal to a CP, a critical point. Is that max min point, right? So right here, I know I got a max min point. But if you look at the second derivative, and second derivative is positive, that means it is concave upward. If you got a max min point, but I know my curvature is concave upward, what kind of point does it have to be? It's got to be at the bottom, which means it's going to be a minimum. And once again, if I got the first derivative equal to 0, which means x equals a critical point, and the second derivative is negative at that point, it's negative second derivative means it's concave downward, and I got a max min point. Well, what kind of max min point does it have to be? It's got to be at the top, which means it's going to be a maximum. This is called the second derivative test. First, you take the first derivative, set equals 0, and solve. And then once you get your critical point, you can just plug it into the second derivative and look at the sign of the second derivative. If the sign is positive, that means the critical point is going to be a minimum. If the sign of the second derivative is negative, the critical point is going to be a maximum. That's called the second derivative test. Now, hopefully you watched the awesome pre-section videos on this section because they're kind of important because they're going to go back and look at a bunch of old college algebra, high school math, algebra 1, algebra 2 material that we look at in terms of figuring out when functions are increasing greater than 0 or decreasing less than 0. So again, these videos I actually did, hopefully on the pre-section video you watched those things. This one I did and this one I did. So I thought we would pick it up with this problem here. One I didn't do on the video. All right. Look at these directions because you're going to see them a lot in this section. F of x is equal to 2x cubed minus 3x squared minus 12x. Some, in this case, polynomial. Part A, find the critical points and the intervals of increase and decrease. Part B, state whether each critical point is a maximum or a minimum. Part C, find the inflection points and the intervals of concavity. And then part D, put it all together and graph it. So you're going to see the power of looking at this stuff through the derivatives. All right, first thing we need to do is part A here. We got to find the critical points. How do you find critical points? You're going to take the first derivative, set it equal to 0, and solve. These guys are polynomials. I don't have to worry about what the derivative doesn't exist at. What is the derivative of 12x cubed minus 3x squared minus 12x? Well, the derivative of 2x cubed is what? 6x squared minus what's the derivative of 3x squared? 6x minus what's the derivative of 12x? 12. There's my first derivative. To find a CN, a critical number, we're going to take the derivative, set it equal to 0, and we're going to solve. Now to solve this thing, I can factor out a 6. That leaves me with an x squared minus x minus 2 equals 0. And because I made up this problem, it's going to factor nicely. Let's take a look at it. 6 times, what times what is 2 that differs by 1? Pretty much 2 and 1. And my sign, because it's minus, I got opposite signs. Since the middle term is minus, the 2 is going to be a minus, the 1 is going to be a plus. Then, you're going to solve for x by setting each factor that has an x in it equal to 0 and solving it. So this leaves me with x minus 2 equals 0 and x plus 1 equals 0, which means x equals 2 and x equals negative 1. These are CNs. But I don't want a CN. I'm supposed to find what? Critical points. What I've got here is the x coordinates. 2 and negative 1. How do I get the y coordinate? What am I going to do? Plug it in where? The original equation. So plug them into the original equation. So this guy right here, this is for your benefit, is going to be f of 2. Plugging it in, it'll be 2 times 2 cubed minus 3 times 2 squared minus 12 times 2. I get negative 20. Plugging 2 into the original function. Now I'm going to plug negative 1 into the original function to get its y coordinate. That'll be 2 times negative 1 cubed minus 3 times negative 1 squared minus 12 times negative 1. I get 7. F of negative 1 is 7. Now these are CPs. That was the first part of my question here. And we're supposed to find intervals of increase and decrease. Intervals of increase and decrease. Anytime in mathematics, calculus especially, you hear the words find the interval, you need to draw a number line. I'm going to draw a number line. And intervals of increase and decrease is a first derivative number line. Just to let you guys know, when I talk about intervals of concavity, concavity is a second derivative number line. This is intervals of increase and decrease. This is a first derivative number line. On this number line, you put your critical numbers on there. In order, because it's a number line. My critical numbers are 2 and negative 1. So here would be negative 1, and here is 2. And what this does is it subdivides the intervals of your number line. Now, to find intervals of increase and decrease, you're going to do something called test values. This is what we teach you guys in high school algebra 1, algebra 2, and college algebra when you guys get there. So you got to pick a number. Now this arrow represents negative infinity. This arrow represents positive infinity. Pick a number between negative infinity up to negative 1. Pick a number in that interval. Negative 2. And I'm going to plug negative 2 into my derivative. Just to remind you, my derivative was the function 6 times x squared minus 6x minus 12. So I'm going to plug in negative 2 into this derivative. This would be, sliding it up, you guys can see this now, 6 times negative 2 squared minus 6 times negative 2 minus 12. And I get 24. Personally, I could care less what the number is. What I'm interested in is what's the sign of it. It's positive. And therefore, everybody in that interval is going to be positive. And what does a positive first derivative tell me? I'm increasing in that interval. Now, pick a number between negative 1 and 2 and use your brain. Good choice. 0. And I'm going to plug 0 into my first derivative, and I get negative 12. I don't care what the number is. What's the sign of it? because everybody in this interval will have the same sign, different numbers, but the sign will be the same, and that sign will be negative, which tells me everybody in that interval has a negative first derivative, which means I am decreasing. Does that make sense? Now, pick a number bigger than 2. I choose 3. You can choose 105 if you want to, don't care, but I'm going to pick something easy to plug in. 3. And I plug in 3 into my first derivative here, so that'll be 6 times 3 squared minus 6 times 3 minus 12. And I get 24 again. I don't care what the number is. What's the sign of it? Positive. So everybody in that interval is positive, which means I'm increasing. But they're going to ask you to state the intervals of increase and the intervals of decrease. Typically, we like to describe this through interval notation. It comes right off your number line. So, what are my intervals of increase? Well, where is it positive first derivative at? Starts at negative infinity and goes to where? Negative 1. Now, when it comes to intervals of increase and decrease, you always use open parentheses, because right at negative 1, you're neither increasing nor are you decreasing, because that's where you actually change, because that's your critical point. So use open parentheses on all endpoints. But wait a minute, keep on going. Union, picking up at 2, going to infinity, I'm still increasing. So it'll be from 2 to infinity. Where is it decreasing at? Between negative 1 and 2. Interval. Notice I use open parentheses for all endpoints. Does that make sense? There is part A. Part A was to come up with the critical points and state the intervals of increase and decrease. Part B was to state whether the critical points are maximums or minimums. You actually use what we call the first derivative test, the intervals of increase and decrease. Look at your critical points. My critical points were at negative 1 and at 2. Look around it. I am increasing, I hit my critical point, and I decrease. What kind of point does that make it? If you go up, hit it, and go back down again. Maximum. So at the point negative 1, this would be negative 1,7, it is a maximum. It will be what we call a local or relative maximum. Look at your other critical point. You go down, hit your critical point, and go back up again. If you go down, hit him, and go back up again, what kind of critical point do you have? Minimum. And because this was a cubic graph, it keeps on going up and down and stuff, these would be again called locals. So that the point 2, which is the point 2, negative 20, this is a local minimum. And that's what part B was. Identify the kind of critical points and you do that right off of the number line. Looking at the increase and decrease. You go up, come back down, that's maximum. You go down, hit bottom, and go back up again, that's minimum. Questions? Part C. Ask you to find the inflection points and intervals of concavity. I'm going to do the exact same thing except on a next level derivative. Inflection points. How do you find an inflection point? You take the second derivative, set it equal to 0, and solve. So I mean my second derivative. Second derivative is the derivative of the first derivative. What's the derivative of 6x squared? 12x minus, what's the derivative of 6x? 6 and derivative minus 12 is 0. To find an inflection point, inflection number, we're going to take the second derivative, set it equal to 0, and solve. So this would be my second derivative, which is 12x minus 6. I'm going to set it equal to 0 and solve. What do I get? I add 6 to both sides, I get 12x equals 6, divided by 12, I get x is 1/2. This is what we call an inflection number. I didn't ask for an inflection number, I asked for an inflection point. So to get your inflection point, you gotta have a y coordinate. What do you gotta do to go get a y coordinate? Plug it back into the original equation. So x is 1/2, so this will be 2 times 1/2 cubed minus 3 times 1/2 squared minus 12 times 1/2. And I get negative 6.5. Now that is an inflection point. They asked me to find the inflection points, and then they asked me to find the intervals of concavity. The key word there is the word intervals. So to find intervals of concavity, anytime you hear the word intervals, you do a number line. For concavity, you're going to draw a number line for the second derivative. And on this second derivative, you're going to put the inflection number on there. What was my inflection number? 1/2. That's where the second derivative was equal to 0. So that kind of subdivides it into 2 spots. And we're going to do test values. Pick a number less than 1/2. Use your brain. 0. And I'm going to plug 0 into my second derivative. Well, don't hurt yourselves. 12 times 0 minus 6 is negative 6. I don't care what the number is. What's the sign of it? It's negative. But remember, this is the second derivative, which gives you concavity. So, second derivative negative means it's concave down, U-shaped down in that interval. Now pick a number bigger than 1/2. I choose 1. And I plug it into my second derivative. That'll be 12 times 1 minus 6, which makes it 6. I don't care what the number is, the sign of it is positive, but a positive second derivative means it's concave up. So they're going to ask for intervals of concave up and intervals of where it's concave down. So let's answer the question. Where is this function concave up at? Again, interval notation, and you don't actually include the endpoints. What would this be? This represents infinity, and this represents negative infinity, so it is concave up between 1/2 to infinity. It is concave down between negative infinity to 1/2, where the second derivative is negative. Does that make sense? So, I have found the critical point, an inflection point, and the intervals of concavity. Now, I want to graph this guy. Left myself just enough room to graph him over here. And this is a very general sketch. So this is part D. We're going to graph this thing. Again, if I wanted more elaborate, I would just stick the darn thing on the calculator and just graph it and declare victory here. We're trying to graph it through analyzing the first and second derivative. So I'm going to plot the critical points. And they're general points. 2, negative 20. So here's 1, here's 2. Negative 20, I'll declare it to be down here. And I'll put a point right there. The other one was negative 1, 7. So here is negative 1, 7 would be right about, I'll declare it to be there to be 7. And here's my point. So here's the point 2, negative 20, and 1, 7. And we got an inflection number of 1/2. 1/2 is right about there. Negative 6.5, which is right about there. And I'll label him as an IP. This is a CP, CP, and this is your inflection point. Now, what I'm going to do here is put my two number lines together. starting at negative infinity and moving over. And we're going to blend these two concepts together. Starting at negative infinity, what is my function doing? It is increasing. Starting at negative infinity, what's the concavity? Concave down. What does increasing concave down look like? I got to go through this point. To be increasing concave down, I got to go up, but I got to be bent downwards. So that's what it looks like in that section. All the way up through negative 1. It's increasing concave down. Once I hit negative 1, now I've got a decrease. But I'm still concave down until I get a half. Decreasing concave down means I got to go down and be bent downwards. So it looks like that. I'm going down and I'm bent downwards. Once I hit 1/2, now I got to continue to be going, I got to continue to decrease, but I'm going to now be concave up. So all the way up to this point, I've got to continue to decrease, but be concave up, means I got to be bent upwards. So that makes it, I'm concave down here, and now I'm concave up. And once I hit 2, now I'm going to be increasing and concave up. Increasing concave up means I'm going up and I'm bent upwards. And this is a general shape of the graph, looking at it from the first and second derivative lines. And of course, you can double check him on the calculator and see if he doesn't look exactly the same. Y equals negative 12x cubed minus 3x squared minus 12x. And I'm going to change my window. So all I care about is right here, negative 1 and 2. So I'm going to go beyond that. So let's try negative 3 to 4. But my y coordinates, I got to make sure I go all the way down to negative 20 and maybe a little bit below that. Negative 25, and I got to go up to 7, so 10's good. And then I kind of scale it according to my picture, and I should see the exact same picture. I'm very happy with this graph. But this is a general sketch. That's all we want. Does that make sense? Turn the page. How nasty can they make this stuff? Well, throw trig at you, of course. F of x is equal to, g of x is equal to x plus 2 cosine of x between 0 is less than or equal to x, which is less than or equal to 2 pi. So all I care about is between 0 and 2 pi. You with me? All right, same directions here. We want to find the critical points and intervals of increase and decrease. Want to find the critical points, the first thing you got to do is you got to take the first derivative. What's the derivative of x? 1 plus 2 is a constant. What's the derivative of cosine of x? Negative sine of x. And we're going to set him equal to 0 and solve. Let's clean that up. So g prime of x is actually 1 minus 2 sine of x. Set it equal to 0 and solve. And it's a trig function. So remember, solve for the trig, then solve for the angle. So I'm going to subtract 1 from both sides. This gives me negative 2 sine of x equals negative 1. Then I'm going to divide by negative 2 on both sides. And this gives me the sine of x is equal to 1/2. Remember, 0 is less than or equal to x, which is less than or equal to 2 pi. Tell me all the angles between 0 and 2 pi where sine is equal to 1/2. Well, one first place is in the first quadrant. What is it? Outstanding. Pi 6. Where else? 5 pi 6. And that's it. It's 2 spots. Pi 6 and 5 pi 6. 30 degrees to 150 degrees for you degree people in here. But for the rest of us to have to use radians because it does say 0 to 2 pi. It's pi 6 and 5 pi 6. You with me so far? These are my CNs. But I don't want CNs, I want CPs. Because we're going to graph this stuff. So what would my critical points be? Well, the x-coordinate is pi 6 and 5 pi 6. Now, because these are nasty looking numbers, because you got to plug it back into the original function, and the cosine of pi 6 is square root of 3 over 2, 0.8660, and they're going to be crappy decimals. Now, I'm going to graph this thing, so I'm going to go decimals on this. So there'll be x, which is pi 6, plus 2 cosine of pi 6, which is square root of 3 over 2. And you end up getting 2.255649583. Now I'm going to plug in 5 pi 6 for x. X is 5 pi 6 plus 2 times the cosine of 5 pi 6, which makes it 0.8859430704. Crappy decimals. Sorry, it's Trig. Does that make sense so far? These are my critical points. But then they also asked me to find the intervals of increase and decrease. Anytime you hear the word intervals, what are you going to do? Draw a number line. You're being programmed. Excellent. It says draw a number line. It's a first derivative number line for increasing and decreasing. But remember, you don't care about less than 0, and you don't care about more than 2 pi. Right? So this is a little subsegment of number line just between 0 and 2 pi. Now I'm going to try to make it relevant. So between 0 and 2 pi is pi. Pi 6 is 30 degrees, which is right about there. 5 pi 6 is less than pi. So it actually, both my little critical points are right there. Does that make sense? So, pick a number between 0 and pi 6 and plug it into your first derivative. What's a number right dead between 0 and pi 6? Well, half it. What's half of 6? 12ths. So let's try, I know it's not a unit circle number, but that's all right, I got calculators. We're going to try pi 12ths, which is right between 0 and pi 6. Pi 12ths, I just divided it by 2. So plug it into your derivative. 1 minus 2 times the sine of pi divided by 12. I get 0.4823. 0.48236, whatever. I don't care what the number is. What's the sign of it? It's positive, so everybody in this interval is going to be positive. It's a very short little interval there. So I'll pick a number between pi 6 and 5 pi 6. I choose, you could choose pi over 3. I would choose pi over 2. 90 degrees, straight up the middle. Okay? And so when I plug it in, it's going to be 1 minus 2 times the sine of pi divided by 2. Now let's see if we can figure this out before putting it on the calculator here. Pi halves is 90 degrees. What's the sine of pi halves? Straight up. It's 1. Okay? Times 2 makes it 2. And 1 minus 2 is negative 1. Yep. Calculator's right. But I don't care what the number is. What's the sign of it? It's negative. So everybody in that interval is going to be negative. Now over here, I have a very large interval between 5 pi 6 all the way up to 2 pi. Pick any angle between the two. I'm going to choose pi because I've already put them on there. So g prime of pi. This will be pretty much 1 minus 2 times the sine of pi. What's the sine of pi? 0 times 2 is still 0. 1 minus 0 is 1. And for those people who don't believe me, fine. Here, 1 minus 2 sine of pi. It's still 1. There you go. Don't care what the number is, it's positive. So everybody in that interval is going to be positive. But they ask you this question. What are the intervals of increase fill in the number line, and the intervals of decrease, fill in the number line. What's my intervals of increase? Where's it increasing at? Between 0 to pi 6, union 5 pi 6. You start your critical points up to 2 pi. And you always use open parentheses on endpoints. Because right at 0, right at 2 pi, you're neither increasing or decreasing. It just kind of deadens and stops. What is the interval of decrease? Between pi 6 and 5 pi 6. Does that make sense? Questions? Okay? All that is part A. You were supposed to find the critical points and intervals of increase and decrease. Part B is actually rather short. State whether the critical points are maximums or minimums. What do we got here? Well, at pi 6, you're going up and then you go back down again. What kind of critical point does that make pi 6? If you go up and go back down again. That's a maximum. So let's just put pi 6 is a maximum. And now I'm going down and then I hit 5 pi 6 and then I go back up again. That makes 5 pi 6 a minimum. Does that make sense? I'll lose you guys anywhere. Now, are these going to be absolutes or relative? I don't know. Wait till the end of the problem. I'll go back and answer that question for you guys. So it's kind of tough to tell. Is this the largest y coordinate or are there bigger y coordinates? I don't know. Gotta go find out. All right, here we go. So that was the answer for just part B, which just state max mins on that, and you just read it right off the number line here. Part C, however, asks you to find inflection points. Here we go. To find an inflection point, I got to take the second derivative, set it equal to 0 and solve. Well, the derivative, first derivative is 1 minus 2 sine of x. Derivative of 1 is 0 minus 2. What's the derivative of sine of x? Cosine of x. So my second derivative function is actually negative 2 cosine of x. I'm going to set it equal to 0 and I'm going to solve. Well, I've got negative 2 cosine of x equals 0. I'm going to divide by negative 2. That gives me the cosine of x equals 0. Solve for the trig, then solve for the angle. The cosine of what angle? Remember, between 0 and 2 pi, the cosine of what angle equals 0. Pi halves, that's 90 degrees, and there's one more. Now, cosine of 2 pi is 1. 3 pi halves, right. 3 pi halves. Know your unit circle. Straight up at 90 degrees, pi halves, and straight down at 270 degrees, 3 pi halves. This cosine of both of those two angles is 0. Okay? But they wanted inflection points. These are inflection numbers. So I got to go back. And I need the y coordinates. To get the y coordinates, I got to plug them back into the original equation. And they're going to be crappy numbers here, so I'm going to go decimal so it's easier for me to graph. X is pi halves. So this will be pi halves plus 2 times the cosine of pi halves. But the cosine of pi halves is 0. That gives me pi halves, or 1.570796. 327. The other point is at 3 pi halves. So it'll be 3 pi halves plus 2 times the cosine of 3 pi halves. Well, the cosine of 3 pi halves is 0 times 2 is still 0. It's 3 pi halves, which is 4.71238898. Those are my points. I happen to have 2 inflection points on this thing. Does that make sense? I lose you guys anywhere. Now we're supposed to state intervals of concavity. For intervals of concavity, I gotta have a number line. Interval means number line. And for concavity, it's a second derivative number line. But the same deal, I don't care about less than 0, and I don't care about more than 2 pi, because I got a domain restriction of between 0 and 2 pi. So my inflection points are at pi halves. Now pi is right down in the middle here, so pi halves would be the middle of that. And the other one is at 3 pi halves. These are my inflection points. So I've got to pick a number on either side of these intervals. So pick a number less than pi halves. I choose pi fourths and plug it into your second derivative. Your second derivative is cosine, a -2 cosine of x. The cosine of pi fourths is square root of 2 over 2 times -2 is negative the square root of 2. Let you know you can use your circle on this thing. I don't care. Okay, fine. It's 1.414. Got the decimals memorized. That's how I got through high school on the trig stuff. I memorized all the decimals. There it is. But who cares? It's negative, which tells me I am concave down in this interval. Pick a number between pi halves and 3 pi halves. You're right. I'm going to choose pi. And plug in here. What's the cosine of pi? -1 times -2 makes it what? +2. I don't care what the number is, and if you really, really wanted to, because you're not so sure about your trig stuff, and you've got the calculator on this stuff, so -2 times the cosine of pi. Cosine of pi is -1 times -2 is 2. It's still there. But who cares what the number is? It's positive, which means I'm concave up in that interval. Now pick a number greater than 3 pi halves. Greater than 3 pi halves, any angle over there in the fourth quadrant will do. I shall choose 7 pi fourths. And when I plug it in, the cosine of 7 pi fourths is once again square root of 2 over 2 times a -2 makes it just negative the square root of 2. Who cares what the number is? It's negative. It's -1.414. But you people that just don't believe me, fine. Fine. This would be -2 times the cosine of 7 pi divided by 4. It's still -1.414. There it is. But it's negative, so it's concave down there. So to answer their questions, where is the function concave upward? And what intervals is the interval concave downward? And this is interval notation right off the number line. It is concave upward between pi halves and 3 pi halves. It is concave downward between 0 and pi halves. Union 3 pi halves up to 2 pi. Remember, 2 pi we cut it off, so 0 to 2 pi. Does that make sense? So there's your part C. Part D asks you to graph. But remember, graphing it, all you care about is between 0 and 2 pi. And this was your original function, f of x, well, it's going to be g of x was equal to x plus 2 cosine of x between 0 and 2 pi. All right, let's plot our points. All right, so here's 0. Pi is somewhere in the middle. Here is pi 6. Here is 5 pi 6. Here is pi halves. And here is 3 pi halves. And I put those on there in particular because these are my critical points and inflection points. Pi 6, 2 point something or other. So the largest y coordinate seems to be 4.7, so you're about around 5. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. There you go. All right. At pi 6, it was 2.25. Pi 6, 2.25 is right about there. That was a critical point. 5 pi 6 is 0.88. 5 pi 6 is 0.88. That's down here. 0.88. These are CPs. The inflection points are at pi halves 1.57. Pi halves 1.57, right about there. And 3 pi halves 4.7. 4.7 is right about there, so it's up here. But because there are two endpoints on this thing, I personally suggest you guys graph the endpoints. So I'm going to plot a couple of extra ones just to make them look good. I'm going to plug in 0 into the original function. Cosine of 0 is 1 times 2 is 2 plus 0 is 2. So this thing starts at the point 0, 2. And 2 pi, just because I want to go decimals, 2 pi plus 2 cosine of 2 pi is 8.28. So 2 pi, the endpoint was 8.28, so it's way up here. 8.28. Now, look at your number lines. Starting at 0 instead of negative infinity, I am increasing and concave down. Increasing concave down means I go up, but I'm bent downwards. And then once I hit pi 6, now I am decreasing, but I'm still concave downward till pi halves. Once I hit pi halves, now I'm going to be concave upward, but I'm still decreasing. Decreasing, but concave upward looks like that. Once I hit 5 pi 6, now I'm going to be increasing the rest of the way, but I'm going to be a concave upward up until 3 pi halves. So increasing concave upward looks like this. But once I hit 5 pi 6, now I got to be concave downward, but I'm still increasing. Increasing concave downward looks like this. And that's the general shape of the graph, looking at it from the first and second derivative number line. And for those people who do not believe me, well, here, be more elaborate then. Knock yourself out. X plus 2 cosine of x. Window is between 0 and 2 pi. My y coordinates look like between 0 and 9. 0, let's see, scale 1. 0 and 9, and I graph it, and there is my shape. And I'm very happy with the look of my picture compared to what the fancy calculator can do. There you go. Does that make sense? Well, how nasty can they make them? Well, let's take a look at number 6. All right. H of x is equal to e to the x divided by e to the x plus 8. So they gave me a more elaborate rational function here, exponential. There we go. But you'll notice in section 4.3 here that all the definition or the directions are the same. Find the critical points, intervals of increase and decrease. Stay whether the critical points are maximum ends. Find inflection points, interval of concavity, and then sketching. This one, you got to be very particular about because you're beginning to see what they're going to do in section 4.4. So here we go. First thing I'm going to do is find a critical point. So I'm going to take the derivative, set it equals 0, and solve. This is the quotient rule. So I'm going to take the quotient rule. Derivative the top, derivative e to the x, times the bottom, e to the x plus 8, minus the top, e to the x times derivative the bottom, derivative e to the x plus 8, well, derivative e to the x, e to the x, derivative a to 0, all over the bottom squared. I'm going to clean this up by distributing. This is going to be e. When you multiply, you add exponent e to the 2x plus 8 e to the x minus e to the 2x divided by e to the x plus 8 squared. Those two terms cancel out, and your first derivative is 8 e to the x over e to the x plus 8 squared. There's my first derivative. But you know what? I should have done this before I even started the problem. Because it's a rational function, I got to be leery of domain issues. So go back and look at the word domain issues. It is a fraction, right? And what you cannot divide by? 0. Look what happens. If e to the x plus 8 equals 0, this would mean that e to the x would be equal to negative 8. Well, it gets rid of an e so I can solve for x. So I'm going to take natural log of both sides. And it gives me x is equal to the natural log of negative 8. But guess what you can't take the log of? Negative numbers. This does not exist. So no problems with domain. Your domain is going to be all real numbers. I don't have to worry about dividing by 0 because when I try to solve the denominator equal to 0, it actually doesn't exist because you can't take the log of a negative number. So here we go. Here is my first derivative. To find inflection points, you've got to take the first derivative, set it equal to 0, and solve. To find critical points, you get first derivative, set it equal to 0, and solve. Sorry. So this is 8 e to the x divided by e to the x plus 8 squared. I'm going to set it equal to 0, and I'm going to solve. How do you solve when you have a rational function? When I have a fraction equal to 0, what are you going to do next? Multiply both sides by your denominator. Clear denominators. So I'm going to multiply e to the x plus 8 squared on both sides. Here it cancels, leaving me with 8 e to the x equals 0 times anybody is 0. It pretty much knocks your denominator completely away. Divide by 8, no problem there. You get e to the x equals 0 divided by 8, still 0. And what kills off an e so I can solve for x? Take natural log of both sides. You get x equals the natural log of 0. What's the natural log of 0? No, it's not 1. Natural log of 1 is 0. Natural log of 0 does not exist because you can't take the log of negative numbers, nor can you take the log of 0. You can only take the log of positive numbers. So, here's the deal. There are no CPs, no critical points on this thing. The derivative doesn't exist. Does that make sense? So, no critical points. So we don't have max min points. But I still need to find intervals of increase and decrease. Intervals of increasing decrease, which means I got to draw a number line. But on my number line, I want to put my critical numbers. Guess what? There are no critical numbers. There are no CNs. There are no critical numbers. So what am I going to put on my number line? Nothing. There are no subdividing. It's one big number line. So pick any number. Use your brain. Pick any number on this number line and plug it into your derivative. I choose 0 because I actually have a brain. 0. So that'll be h prime of 0, which would be what? H prime, which is 8e to the 0. There it is. E to the 0 divided by e to the 0 plus 8 squared. E to the 0 is 1 times 8 is 8. E to the 0 is 1 plus 8 is 9 squared. It's 8 over 81. I don't care what the number is. What's the sign of it? It's positive, which means everybody on this number line is positive, which means where is it increasing at? Negative infinity to infinity. Here's negative infinity, here's infinity. Where is it decreasing at? none, I believe is what WebWork wants you to type into this thing. It's not decreasing anywhere. Does that make sense? No answer. Officially, you put the empty set thing there, but none or leave it blank or something like that. Read your WebWork directions. Does that make sense? All right. Let's keep on going. What about, well, I don't have to worry about, this is part A. I don't have to worry about part B. What kind of max min points you have? You don't have any. So keep going. So what's part C? I got to have inflection points. So I need the second derivative. The second derivative is the derivative of the first derivative. It's still a quotient, so I got to use the quotient rule. It's a little nastier here, but here we go. Derivative of the top. Derivative of 8e to the x is 8e to the x. Derivative of e to the x is e to the x. Derivative of the top times the bottom, e to the x plus 8 squared, quotient rule, minus the top, 8e to the x, times derivative of the bottom. Take derivative of the bottom, I got to use the chain rule. Derivative of the outside, the inside, e to the x plus 8 stays the same, raised to the first power, times the derivative of the inside. What's derivative of e to the x plus 8 is e to the x. Derivative of e to the x, e to the x, derivative of 8 is 0. All over the bottom, e to the x plus 8 squared, squared. The bottom squared. Clean it up. This is equal to 8 e to the x times e to the x plus 8 squared. Cleaning this up, 2 times 8 is what? 16. E to the x times e to the x would be e to the, tell you what, I'll do it this way. E to the x times e to the x. I'll put 2 of them there. And then times e to the x plus 8 over e to the x plus 8 squared. Squared is to the 4th power. Because here's your trick. Clean him up. What do you have common in the numerator? There are 2 terms in the numerator. What do they both have in common? You can factor out an 8. You can factor out an e to the x. And you can factor out an e to the x plus 8. You can factor out an 8, e to the x, and an e to the x plus 8. And you would be left with, well, remember this was e to the x plus 8 squared, so you're left with another e to the x plus 8. You're left with a minus. Factoring an 8 out of 16, you're left with a 2. One of the e to the x is still there, but that term is completely gone. Over e to the x plus 8 to the 4th power. This is beautiful algebra is really what I'm doing here. I factored out what they had in common. Now, what cancels? E to the x plus 8 cancels with 4 of them, leaving you with 3 of them. So when you clean this up, you're left with 8 e to the x times e to the x minus 2 e to the x is negative e to the x plus 8 over e to the x plus 8 cubed. That is my second derivative. Now I want to find critical numbers. Excuse me, inflection numbers. I want to find inflection numbers. I want to take the second derivative, set it equal to 0, and solve. So here we go. 8 e to the x times negative e to the x plus 8 over e to the x plus 8 cubed equals 0. How would you solve this thing? What you going to do next? I'm going to multiply both sides by e to the x plus 8 cubed. Does that make sense? This cancels, leaving me with 8 e to the x times negative e to the x plus 8 equals 0 times anybody is 0. Now I'm going to set each factor that has an x in it equal to 0. E to the x equals 0 and negative e to the x plus 8 equals 0. Solving, so here when I solve, I get 8 equals e to the x. What gets rid of an e? Natural log both sides. Here you get x equals the natural log of 0. Well, what's the natural log of 0? Does not exist. Here, you take the natural log of both sides, and you actually get x equals the natural log of 8. That is your inflection number. So to get the inflection point, x is the natural log of 8. I'm going to plug it back into the original function. Now let's see if we can do some math in our head. E to the natural log of 8. E and natural logs do what to each other? You do stuff with 8. E to the natural log of 8 is 8. 8 plus 8 is 16. It's 8 over 16. What's 8 divided by 16? Yeah, it's a nice number. It's 1/2. You get a natural log of 8 comma 1/2 is your inflection number. So here we go. Let's finish this thing up. So to get your intervals of concavity, you got to put your inflection number on there. Natural log of 8. Now, pick a number, use your brain, less than a natural log of 8. How about 0? Natural log of 8, some crappy decimal. So, plugging in 0 into your second derivative, and remember your second derivative is right here, e to the 0 is 1. E to the 0 is 1. So this will be 8 times 1 times negative 1 plus 8 is 7 times 7 divided by e to the 0 is 1 plus 8 is 9 cubed. You get 0.0768. Who cares what the number is? It's positive. Now pick a number greater than the natural log of 8. Well, I don't think 1 is going to do it. Natural log of 8 is actually 2.07. 3. How about just 3? So h double prime of 3 would be, plugging it in here into my second derivative, 8 times e cubed times parentheses negative e cubed plus 8 divided by parentheses e cubed plus 8 cubed. You get negative 0.087. I don't care what the number is, it's negative. Does that make sense? Which tells me that it is concave up on the interval between negative infinity to the natural log of 8, and it is concave down on the interval between the natural log of 8 and infinity. Now, if you graph this thing, there's only one point that you actually want to graph on this guy, just to let you guys know, and that's the natural log of 8, 1/2. And actually, if you graph this thing, it's a graph that's going to be between 0 and 1 because it's always increasing. And you can talk about your horizontal asymptotes things here. So as you go to negative infinity, this thing goes to 0. It's increasing and concave up, and then it goes increasing, concave down. This is what your graph ends up looking like. And again, you can actually double check him on the calculator. Now, we've still got a little bit of section 4.3 left to do. And the reason why I wanted to do this is because I heard there was a problem on the section 4.4 pre-section video. I'm going to go see if I can't fix that thing up, and I will put the pre-section video due at the beginning of next class. So I'll buy you some extra time on this and see if I can't get that video working for our class. All right? Well, we got to pass back these tests, so hold on just a second.